Alright, so in this video, I'll be talking about how I implemented the MIPS32 data path using Verilog. So here is the entire pipeline for the MIPS32 data path. And let me zoom in here and show you each of the stages. So we start off with the PC reg, goes into the ROM, reads the instruction, and it goes through basically the 5 MIPS stages: the IF, the ID, the EX, the MEM, and write back. And of course, in between those stages, we have the intermediate registers, such as IFID, IDEX, that's gonna hold the values from the previous stage and pass it off into the next stage. And last but not least here, we have the RAM down here, that's gonna be used for the memory access operations. All right, so that's the whole diagram. And then let's go into Quartus and check my Verilog code to see how I implemented this diagram into code. Okay, so here we are in Quartus. Now I have a bunch of files open, and each of these Verilog files represent a block in the diagram. So I have the PC reg, the ROM, ID, IFID, and so on. So let's go through each one of them and see what they do. So here's the PC reg. All it's gonna do is basically count up by 4 so that it can read up to the next instruction. And the ROM here, this one is the one where it holds the list of instructions. I made it read from another file called insmem4.data, and let me show you what that data looks like. Alright, so here is the insmem4.data, and what this is trying to simulate is this assembly code on the left. Now you can pause this video and try to look at it and figure it out for yourself if you'd like, but all it's gonna do is it's a nested loop, and it's going to try to add values of R4 over and over again until the value of R4 reaches 150. So the machine code on the left here, you just basically copy that over into a normal text file and then save it as insmem4.data. So that's the file the ROM is gonna try to read off of. Okay, so let's go on to the next part. Next we have IFID. It's an intermediate register that's gonna pass off information from IF to ID. Then we have the decode stage where it's gonna divide up the fetch 32 bits into different parts such as opcode and RS and RT, and so on, to determine what kind of instruction they are. Now here we have all the list of all the instructions here. And then we have another intermediate register, IDEX. Then we have the execution stage where it's actually gonna do the operation. So we have a always block for logical operations such as AND and OR and so on. And then we have another block for shift operations, and we have the last block for arithmetic operations. Then we have another intermediate register. Then we have MEM. Now MEM is gonna work together with RAM to do memory access operations such as load word and store word. And then we have the last intermediate register, that's gonna be MEM write back. And then this is gonna pass off the information into reg file if they choose to do so. And here's MIPS32. This is the top module. This is the module that's gonna combine all the previous modules into one big chunk. So I have a list of all the wires that I'm gonna use to connect all the previous parts together. And I call all the previous modules here, and I connect all the ports accordingly. And then the last file here is the MIPS32 test bench. Now this is where I generate a clock signal, and I simulate a reset signal as well. I'm gonna activate the reset signal for 100 cycles, and then I'm gonna deactivate the reset signal, and that's gonna be the cue for the operations to actually start working. Alright, so that's it for the code. Let's see if the RTL viewer creates a correct diagram. Okay, here we are in the RTL viewer. So it doesn't look as nice as a nicely drawn diagram like this because it's computer generated. but all the wires seem correctly connected, and there doesn't seem to be any like weird connections to ground or anything like that. I actually checked each individual wire before, and they all turned out to be fine. So let's go on to the wave simulation and see if we get the correct result. Okay, here we are in the wave simulation. Now there's a whole bunch of signals here. We have the clock, we have the reset signal that starts over here at 100 nanoseconds. And the signals to pay attention to here are the reg files, the registers R1 through R4. Why those four? Because the loop that I had before only deals with those four registers. Now, to understand this loop a little bit easier, here's the C equivalent. Basically, what's going to happen is the value of R4 is going to get added up and up and up until it reaches 150. And the value of R4, it gets added up from R3. So you add the value of R3 onto the previous R4. So let's see if it works correctly. So the line we're going to pay attention to is this one, R4. Starts off at 0. And then the value of R3 gets updated to 1. And we're going to add the value of 1 onto R4. So 0 plus 1 is 1. And then 1 plus 2 is 3. 3 plus 3 is 6. So on and so forth. And then let's see if it reaches the value of 150. Alright, so around 6650 nanoseconds, it reaches the value of 150. So it looks like everything's correct. Alright, so that's how we implement a MIPS32 pipeline using Verilog. Thank you for watching.